Jose. Okay. So on Saturday, you have section 3.6 in MyLab math to get done. And then you also have your second review to date to finish and Gmail it to me. So send it, scan it, and send it by Gmail. Then Sunday, you have quiz 4. That's sections 3.5 and 3.6. 13 problems again. The quizzes are a lot shorter than everything else. No, 7 problems, whatever you had last quiz, same number of problems. And then don't forget, you can schedule that second exam with ProctorU at any point in time now for the end of next week. So, did anybody have any questions about the transformations? I was so excited because everybody did it. All 5 people in the course that are still actively involved did that assignment. I was so pleased. Yay. Any problems with the transformations, though? Looks like we're all good.
No. Yep.
Yay. It's fun to do, especially for those of you that will move on into pre-calculus next. You'll use those ideas of shifting graphs with the trigonometric graphs, and that's always fun too. So, okay, so today we're going to do section 3.6 on building functions. This wraps up chapter 3 for us. We'll start chapter 4 next week. We will also finish chapter 4 next week. We only do 3 sections in it. It's a really short chapter, so it will also be on the exam next week. I did email out the notes, so I'm going to read example 1. And as we walk through it, we're going to kind of do what they're looking for as you build a function. So example 1 says, let P be a point on the graph of y equals x squared minus 5. So I have the graph of y equals x squared minus 5. And I'm just going to stop right there and tie this to yesterday's lecture. So what does the graph of x squared minus 5 look like? So that's one of our toolbox functions, x squared. And that minus 5 is going to shift it how?
Down 5.
Beautiful. So I'm actually just going to draw a really quick sketch. 2, 3, 4, 5. So there's that vertex or minimum. And then I'm going to draw that parabola in. So that's the graph of y equals x squared minus 5. What they want us to do is to pick a point on that graph. And you can pick a point anywhere on that graph. I'm just going to put it where it's easiest to deal with. So I'm just going to pick a generic point right down here somewhere. And we're just going to call that x comma y. And they've labeled that as point P. So that's our point P, and it's at x comma y. I agree that it's a negative x and a positive y, but that comes out at the end of it, so I don't need to worry about that. And then I'm going to continue reading. It says, let's express the distance from the point P to the origin as a function of x. So we need that distance as a function of x. So I'm going to draw that distance in. So what we're looking for, and I'll use the red again, we're looking for, here's the origin, and we're trying to find that distance d that we've shown on the picture. Well, good thing we know a distance formula. So we need to find the distance between the point x comma y and the origin, which is 0, 0. So we're just going to go to the distance formula, which we've done before. And I'm going to write the formula again just to remind you because it's been a week. So it's x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And that's the distance formula. So we have 2 points. We can plug them in. I'm going to use point P as the x2's because it just looks nicer. So we're going to take x minus 0. So that's the x coordinate of P minus the x coordinate of the origin, quantity squared. And we'll do the same thing with the y coordinates. So we end up with y minus 0 quantity squared. So again, that's this x minus this 0 and this y minus this 0. And then you square. Well, we're going to clean that up just a little bit. Those zeros are kind of meaningless. That's really just x squared plus y squared. So far, so good. Okay, at this point in time, what we need to look at is the fact that it's asking us to write this as a function of x, and this is where the sneakiness comes into play. If this is a function in terms of x, that means the only letter or variable we can have on the right side is x. So we need to replace y somehow. We need to get it out of that function because they want the function to have x's only. So this is where you look around and find the other information that you've been dealing with. So what we have is we know that y is equal to x squared minus 5. So I'm just going to come in and take this y and replace it with what we know y is equal to. Since I'm on this curve, I know that anywhere on the curve, the y is going to be equal to x squared minus 5. So we're going to replace the y. That's going to give me x squared plus, and then in place of the y, we'll put x squared minus 5 on b squared. And now we have a function in terms of x. Now, if this were a face-to-face and you were turning homework into me, I would let you stop right there. But I noticed that in MyMLab Math, you need to clean that up. So I'm going to go ahead and FOIL out the x squared minus 5 and start collecting like terms. So we're not quite done only because of how they want the information inputted. If we FOIL out x squared minus 5 times x squared minus 5, we'll get an x to the 4th minus a 10x squared plus a 25. So x squared plus x to the 4th minus 10x squared plus 25. So all I can do to clean that up is add my x squared terms together. So I end up with an x to the 4th. I'll have a plus 9x squared and then plus the 25. And there is my function in terms of x. So they even told me what letters to use. So d of x is equal to the square root of x to the 4th plus 9x squared plus 25. So the theory is now is that if you give me a point, I can tell you how far from the origin it is. Okay, the key to this more than anything else is they're going to tell you how to start the problem. They'll use a basic formula, either distance or maybe area or something like that. You then, once you've done that, need to do a replacement in terms of the y value. So they will have given you something else to replace that y value with. So substituting it in, you can then clean it up and get a function in terms of x. There is a part B to this problem, but is everybody okay with part A? That was part A.
Yes.
Good. Okay, part B, and I need that, so I'm going to erase up here. Part B says, what is that distance if x is equal to 0? So they're asking if x is equal to 0, we need to find that distance d. So I'm going to simply take my formula and plug in 0 for all the x's. So that would be 0 to the 4th plus 9 times 0 squared plus 25. Well, all the zeros are going to cancel out. We just have the square root of 25, which is 5. Well, that was interesting. Why did that come out that way? So nice and neat. Okay, well, if x is 0, aren't you right down here on top of the x-axis? So if x is 0, I'm right down here, and I already know that that's 5 units down. So what we literally just found was that distance by moving p down here to that point. So it does make sense in hindsight as to why it comes out. So you're going to have one on your homework that's very similar to this one. The only thing that's going to change is that beginning equation. It could be x squared minus 7. It might be x squared minus 3. It's just going to be a different parabola that you'll be working with. I think those are fairly friendly function problems. Okay, on to example 2. So example 2 tells us that a right triangle has one vertex, that means corner, on the graph of y equals 16 minus x squared, where x is greater than 0 at a point x comma y. Another vertex corner at the origin. And the third is on the positive x-axis at x comma 0. We want to express the area of the triangle as a function of x. And it probably just sounded like I was just saying Greek or Latin to you, because that's what it's going to sound like. So we're going to take it apart one little piece at a time. So it says we've got a right triangle, and it's inside the graph of y equals 16 minus x squared, and that's x greater than 0. And we'll talk about that in just a minute. We're going to do the same thing here we just did. We need to graph that. It, again, is one of our toolbox functions that's been shifted. So what is that 16 doing to that parabola or that U shape? So it's 16 minus x squared.
Is that the y-intercept, is the 16?
Yep. So we're going to be up here at 16. Now, the x squared has got a negative in front of it, so instead of opening up, it should open down. So what I'm going to do is just literally draw a parabola starting at that 16 that opens down. And that's y. Y is equal to 16 minus x squared. So notice that it's written differently than we were writing things yesterday. but it still works. Okay, now what they're telling me is that I've got a right triangle sitting inside of this parabola somehow. They tell me that one corner is at a point x comma y, and they are telling me that x is positive. So that's what this is telling me. So I'm simply going to put the point x comma y into that first quadrant because it just makes the most sense. So they're telling me to put my point somewhere in here. So here's our point x comma y. So one corner is on the graph. It then goes on to tell me another corner or vertex is at the origin. So I can put another point right there. And the last comment says the third corner is on the positive x-axis. So I'm just going to drop a line right down and make a point. And there's my right triangle sitting in there. So it's this little itty bitty triangle right in here, but it is a right triangle. So you have to get that picture from all of their words. And I think that's the hardest part about the assignment is to draw the picture. So any questions about drawing the picture from the words? Good. Assume we're good then. Okay, what they want us to do is to find the area of that triangle. So we need the area of the triangle. And again, they want it in terms of x or as a function of x. So, as a function of x. Okay, well, ignoring the x part, what's the formula for the area of a triangle? 1/2 the
Base times height.
Beautiful. So now we have to figure out what's the base and what's the height of our triangle. Well, this little distance in here is going to be our base. This distance over here is our height. And for a triangle, the height is always the perpendicular distance from the bottom to the top. And so because this is the right triangle, we know that this is the bottom and this is the top. Well, that's great, but we need it all in terms of x. So let's take it one step at a time. I'm going to keep the 1/2. What is my base? Well, if I'm over a distance and at this point x comma y, isn't this base down here really the distance x? That's how far over I've gone. In terms of a height, well, you're up at a height of y. So the height is equal to y. So instead of using the base and the height, we're just using x and y. Any comments on that?
No.
Yes, good. Okay, so then all we have to do is replace y. So now we're going to come in, replace y because we have to have a function in terms of x only. So we have a of x is equal to 1/2 x, and in place of the y, we'll go back and pull out the fact that we know because we're on the curve that y is equal to 16 minus x squared. So I'm going to go ahead and clean it up because the program wants you to clean it up. I'll distribute the x in first. That would be 16x minus x to the third. And then I'll distribute in the 1/2. So 1/2 of 16 is going to give me 8x. 1/2 of the x cubed I can't do, so I'm just going to write it as minus 1/2 x cubed. And that's our function in terms of x. So we're done. We did exactly what they said to do. And you'll do one similar. You'll either put a triangle or you'll put a rectangle in there. And putting a rectangle in there only takes off the 1/2, so it's not that much of a difference in terms of a problem. Any comments or questions? We're doing good.
I'm good.
Yay! Okay. Example 3 says that a rectangle is inscribed in a circle of radius 2. And we know that the circle is centered at the origin, and there's a picture there telling us that. So basically, we're out 2 units. We've got a circle. Inscribed means totally inside. So totally inside of that, we have a rectangle that is sitting there. And the rectangle is kind of centered also around the origin. And that's why there's a picture there, because my picture is never very good. Okay. It says, let P be the point in quadrant 1 that is a vertex or corner of the rectangle and is on the circle. So this is our point up here. Here's P, it's x comma y. So you can tell me it's in quadrant 1 this time. They want us to express the area of the rectangle as a function of x. So we want the area as a function of x. Now what's going on here is the same thing we just saw with the triangle. We know that this distance right here is x, and we know that this distance is y. So when I go to write the area of that rectangle, we know that normally it's the length times the width. So the width is fairly straightforward here. Well, no, I guess they're both the same thing. Because the x and the y are only the distance that you are out in the first quadrant, to get the total width all the way across, it would be twice x. And to get this total distance over here, it would also be 2y. Does that make sense? You're doubling them because this time we're going all the way across. Okay. So then our length is going to get replaced with 2x. Our width is going to get replaced with 2y. So we end up with a 4xy as the total area. Well, that's wonderful. So far, so good. The problem is that, again, they want you to write it as a function of x. So we have to somehow or another get rid of y. Okay, well, so this is the first problem where they didn't give me an equation to help me get rid of the y. So I have to go figure out my own equation that I'm going to manipulate to get rid of that y. So what we do know is that we have a circle. And we know from our previous chapter that the equation of the circle is x minus h squared plus y minus k squared is equal to r squared. Because this one is centered at the origin, the h and the k are zeros. So what we have is x squared plus y squared. And they already told me the radius was 2, and 2 squared is 4. So they didn't give me a second equation, but they gave me a means to write that second equation. Because we want to get rid of y, we need to solve this for y. So we want to solve for y. So I'm solving for the letter that I need to get rid of in my area function. So y squared would be equal to 4 minus x squared, and y is then equal to the square root of 4 minus x squared. Okay, now what? Well, now we're just going to do our replacement. So down here, we're going to take that area in terms of x. I have a 4x, and in place of that y, I'm going to replace it with the square root function of 4 minus x squared. So I end up with 4x times the square root of 4 minus x squared. There's a lot of 4's floating around there. That's only because the radius is 2. And that's your answer. So you've now written a function in terms of x that expresses the area of that rectangle that's inscribed or inside of the circle. So you're going to do the same kind of one, but you're going to have a semicircle. It's only half of this. The difference is that instead of having 2y for this dimension, you just have a single y. So you'll have 2x because it's all the way across, but you'll only have a single y sitting there, and it's a different radius, so it's going to change the output at the end, but it's very, very similar to this one. So let's walk through that really quickly again, just to make sure everybody's got it down. So what we're looking at is the fact that we know the area is the length times the width, so that let me write a function in terms of both the x's and the y's, but because we've got a y and they want the function as x, we have to get rid of the y. So I then had to write a second equation where I solved for y so that I could substitute that into the area function. And that's kind of a theme that we'll be doing, is this substitution throughout all of them. Okay, any comments on that one? No. Okay. Nobody stopping me means I can move on. Okay, example 4 is one of the homework problems. I think all they will do is change the numbers on it. So, but there's not another one in the book for me to pick up and use, so I'm just going to use their problem out of the textbook. Yours should be similar with different numbers. So there's a picture that accompanies this. It says an island is 2 miles from the nearest point P on a straight shoreline. So we basically have a straight shoreline, which I've never seen, and then sitting out here is an island, which is point, yeah, no, that's not point P. It's just the island. So I guess I'll call it I for island. Point P is where we're going to shore. That is a right angle sitting there. Okay, a town is 12 miles down the shore from P, so I'm going to call this T for town, and we know that that total distance is 12. So If a person can row a boat at an average speed of 3 miles per hour, so we can row at 3 miles per hour, and the same person can walk at 5 miles per hour, they want me to build a model that expresses the time as a function of the distance x from P to where the person lands the boat. That just looks like a bunch of gobbledygook. So what's really going on here is what you could do is you could, if you were here, row the distance to P and then walk the distance down to the town. But it makes more sense to decrease the amount that you can walk because that's slower. So what we're going to do is we're going to row to shore over here and then walk the rest of the distance. So this is where we're actually going to land on the shore. So the idea here is we're trying to minimize the amount of time it takes. Okay, now what the picture does show you is they show you they're going to call this x, and then this side of it is 12 minus x. So if this distance is x, the total distance is 12, and this side of it is 12 minus x. They've also on the picture labeled this is 2 miles, and then they call this D. They call it D1, and they're calling this over here D2. So D1 is the distance that you're rowing, and D2 is the distance that you're walking. So I guess I'm going to line those up. So we're going to row 3 miles per hour, and we're going to travel that as a D1 distance. This would be D2. Okay, that's all the background information. Let's see if we can get a handle on what they're asking for. So they want us to write a function t in terms of x. So this is time in terms of x. Okay. We do know that distance is equal to rate multiplied by time, and we did this just yesterday. We said that if we divide both sides by r, then we get that d over r is equal to t. So the total time is going to be equal to the distance that you row divided by the rate that you're rowing, plus the distance that you walk divided by the rate that you walk. So on their picture, they've called the distance that you're rowing D1. The distance that you're walking is this 12 minus x, or D2. So right now we know that this is D1 over 3, because that's the rate that I row at, plus the distance we walk is 12 minus x over 5. Any comments to that point? The problem is they want this as a function of just x. So in this case, I have to get rid of D1. It's not a y, it's a distance that I have to get rid of. So I'm going to come back in and take a look at the right triangle that involves D1. So I know that up here, there's a right triangle. It's got D1 and x and a 2. So I can use the Pythagorean theorem to figure out what D1 is. So I'm going to drop the subscript at this point. So from that right triangle, we know that D squared is equal to x squared plus 2 squared. So again, that's this right triangle up here. It's the 2 squared, the x squared equals to the d squared. Okay, well, d is what we need to get rid of, so I'm going to solve this for d. So d is going to be equal to the square root of what, x squared plus 4? And then all I have to do is substitute that d in for my d1. So that would give me the square root of x squared plus 4 all over 3. Plus 12 minus x all over 5. And there's the time it takes in terms of x. So that, I think, is an ugly problem, only because it's hard to get a handle on the picture. So hopefully that helped. Any comments or questions about that? I'm looking at the book. They then come in and ask you, how long will it take if you land the boat 4 miles from the shore? So once you've got this, they're going to have you come in and plug in different values for x. So, but I think, again, what they'll do is change some numbers on yours in the program. So, okay, any comments about that one? It's the hardest one. It's the last one on the assignment. Okay, just to make sure we have examples of everything that you are going to do. Example 5. gives us an open box with a square base, is to be made from a square piece of cardboard that's 24 inches on a side by cutting out a square from each corner and turning up the sides. Express the volume of the box as a function of the length of the side of the square cut. And again, I'm sure it just sounds like I'm saying blah, 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 blah. It's a good thing you got it and you can read it in front of you. Okay, so what are we starting with? Well, there's a picture there. The picture does help. So I've got a square piece of cardboard. It's 24 inches on each side. So it's 2 feet on each side. It's a pretty good size. Okay, what we're going to do is we're going to come in and cut out this corner, this corner, this corner, and this corner. We're going to cut those out. And then what we're going to do is we're going to fold it. And I'm going to fold it along this kind of T shape that's sitting in here, or plus shape that's sitting in here. We're going to fold along those red lines. And when I do that, I'm going to get basically a box. So this is not how boxes are made because they're not structurally sound, but it's the beginning for a box. They do tell us that the piece we're cutting out is length X. So this little piece is X by X. Okay, they want the volume of the ending box, nothing to do with the piece of cardboard other than it's been cut up. And we know that volume is length times width times height. So what we need is the length of the box. So we started off with 24 inches all the way across. We're going to cut off X on this side and we're going to cut off X on this side. So then what's this little piece that's in the middle? Well, I had 24, I cut off X and I cut off X. So does everybody see that that's then 24 minus 2X? And that's the length of the box. Now, the width of the box, because it's a square piece of cardboard, is going to be the same thing. So it's the 24 that's sitting on this side. We're going to subtract off X. We're going to subtract off X. And the width comes out to be the same thing. Now, what about the height of the box? How tall is this box? Well, if we cut out this little X and then fold this piece up, isn't this X that we cut out the height? This is visually hard. And there it is. So there's our volume in terms of X. Now notice we don't have to do any substitution on this one at all. I'm sure that in MyLab Math, you would have to multiply this out. But because we need this for a future problem, not for this section, I'm not going to worry about multiplying it out. We'll leave it alone and call it good. Any comments about the 24 minus 2X? At this point, you probably have done that somewhere in your math career. Okay, example 6 is our last one. You do have one something similar to 6 though. Again, I think the problem with 6 is it's a visualization problem. Okay, so we've got a wire of length X. So I've got a piece of wire and I know it's X inches, centimeters, feet long, it's X. Okay, we are going to bend it into the shape of a square. So there's a typo on my handout that I didn't catch until I keyed it up. It's the shape of a square. Because in part A, it wants us to express, that's an A, the perimeter of the square as a function of X. Okay, let's get a handle on what's going on. I've got a piece of wire. I'm going to take that piece of wire and I'm simply going to make it into a square. So I'm going to bend it so that it's a square shape. So they want the perimeter. Isn't the perimeter the distance around the outside? So if I take this whole piece of wire and bend it to make a square, then haven't I used the entire X to make the square shape? So that means that your perimeter is just X. That's it. Huh. That was an easy part A. Part B wants us to find the area as a function of X. So this is a little more challenging for us. Let's go find an area. Well, we know from our formulas that the area of a square is the length times the width, or the side squared, because they're the same on a square. Well, I need that to be in terms of X, so I have to stop and think about this. So if I took this X and made it into a square, how long is each side?
1/4 X?
Yep, that'll work. Exactly it. And so we're just going to take that and substitute it directly in. So we'll take 1/4 X and then we're going to square it. So 1 squared is 1, 4 squared is 16, X squared is X squared, and that's it. There's your area function in terms of X. Okay, now the one you guys are going to do on the homework does the same thing with an X, but it uses a circle instead. So I gave you the circle one on the homework. So just as a reminder that when you deal with the circle, you need a couple of formulas. Does anybody remember what you call the outside distance around a circle? It's not a perimeter. When it's a circle, what do you call that?
Circumference?
Yeah. Circumference. That's exactly it. So if you're starting off with a wire of length X, then wouldn't the circumference just be X? So that's part A on the problem. We just half your homework. Okay, the harder part is the area. Does anybody remember the formula for the area of a circle? Pi r squared. Okay. So we also know that the circumference is 2 pi r. Does that make sense to everybody? Okay, so what are you going to do? You need to write this area function in terms of x. Well, we know that x is equal to 2 pi r. Can't you solve this for r and then substitute it in down here? So if you solve this equation for the circumference in terms of r and plug that in down here, you'll get an area in terms of x. So that's the one that's on your homework. Okay, and those are the building of the functions. So there are a lot of other ones in there, but they're really kind of ugly. And what the book is trying to do is define as max and mins, which we haven't talked about on the calculator. And we leave that for pre-calculus. So we're very limited on the ones that we can assign. Okay, and that's it. That wraps up chapter 3. It's one of our longer chapters. So it took us a couple of weeks to get through it. We'll get through chapter 4 next week, and then we can move into chapter 5. And in case you haven't recognized it yet, at the end of next week, you're halfway through the course. Woohoo! Yay. Any comments or questions about anything we did?
I'm okay.
Nope.
Are we good?
Yep.
Okay, well, have a great
Good.
weekend. Don't forget you have stuff due on Saturday and you have stuff due on Sunday. And don't forget your discussion. Nobody, as of last night, had posted a discussion yet, but you have an application discussion that's due this Sunday also. So you need to go in and work one of the variation problems and get it posted for me. So have a great weekend, and I will see you on Monday. We do have class this Monday. We'll start chapter 4, okay?
Me
Thank
too.
you.
Thank you.
Bye-bye.
Have a good one. Bye.